Hello and welcome to lecture 13. Today is a fun lecture. We're going to do a case study. We're going to do a couple of these in this quarter. So what I mean by that is we're going to design a specific component and not just show designing a component, but show this iterative process of building something really simple and then incrementally extending it, revising it, improving it. And emphasis not only on just examples of using chisel in practice, but also the process, right? How do we take this goal we have, shrink it down to something manageable, get that first thing built, get that bootstrap, and then build our way up from there. So for the thing we're going to be case study today, it's going to be a queue, right? So these five bows we saw earlier, we saw using the standard library version previously, and of course, from here onwards, you should use the standard library version. But today we're going to show how you might go about designing your own and the iterative design process of getting there. And by the time we're done, our end result is actually pretty similar to what's in standard library. But we're going to see how this really nice polished code that exists, how is that ever written? We're going to show how to get there incrementally. It doesn't just come out of nowhere. Okay, so this entire course, one of the main themes is designing for reuse, right? We want to build generators, we want to make reusable code, all in the hunt for productivity, right? And so I think we're talking about how to design a queue and how do we iteratively improve that queue. So we can go ahead and fire up a notebook. So when we're designing for reuse, right, we need to kind of identify what do we think are use cases for both the current problem as well as users we hope to support, and then figure out how to kind of do that. And so it's really about recognizing what is the not just the functionality, but the pattern functionality. Or it's me, a family of functionalities that are very similar. Hopefully, our generator kind of can support all of them. How do we recognize that pattern? And how do we figure out, okay, for that pattern, what is necessary parameterization, right? If there's parameters that really the user should need to think about, we can figure out internally, we should figure out internally, right? And what's kind of the minimum we have to expose and how to actually support users for what we need to do. So, like I said, today's all about this process, right? So what's the process? We don't want to just spend, waterfall style weeks and weeks and weeks of doing designs, weeks and weeks and weeks of doing design reviews, and then, build it block by block and, build each block independently, test each block independently, put them all together and hope the whole thing works, right? That's not what we want to do. We want to do this, agile approach, incremental, right? We're going to build something simple. It's going to be somehow lacking. It's going to be lacking functionality. It's going to be lacking optimizations, you name it. And we want to figure out a way to incrementally kind of keep adding on what we need, right? And so like I said, the whole goal for this course, keep showing that logo, right? Close the loop, right? Get something working. For today, it's going to be getting a simple design running in simulation against a test bench. And then we're going to go ahead and keep, tweaking it. And we go ahead and change design. That may require a change in a test bench too. And then kind of keep repeating and keep extending. Um, and so like I said, the kind of the key steps in this progressive design process, number one, how do I get started? What is the simplest thing I can build to get going? And then how can I test it? And then not just in the beginning, but also as it evolves, right? It can be very hard if you have this entire project and you build it without testing, and then someone else later on tells you, make some tests. You're like, well, I can do this, whole integration test of the entire thing running, but testing a module is kind of hard because there aren't really nice modules. If you do testing for the entire lifetime, you will see how to change your module boundaries and such that it makes it easier to kind of test the pieces individually and integrated. And that's the thing. So even though I talk about this whole narrative of, oh, we're going to do things progressive, we don't know for sure what the right answer is. We're going to be kind of constantly evolving, constantly adapting. Just because we're constantly evolving, constantly adapting doesn't mean there's not a plan, and there shouldn't be a plan. It just means you're able and willing to change along the way, right? So, chart a roadmap, right? Here's my end goal I want to get to. How do I get there from something simple? And how do I get this progressive set of steps to get there? Kind of incrementally adding on a feature, incrementally adding on optimization, perhaps have more restricted level of testing and make sure that works to get there, right? And so this is what we're going to be thinking about not just for today, but you'll also, of course, be doing this in your projects. Um, our good friend, the Q, also known as a FIFO, first in, first out, right? So we covered this already in the course as an example of something using these decoupled interfaces, right? So these interfaces, even though we label as a single arrow going one direction, we know internally it's got, within the decouple it has the bits, the actual payload, as well as ready valid signals. And between ready and valid, those wires are going opposite directions. So there's actually quite a few wires here. And yeah, if you want to build a queue, of course, it has the NQ side where things come in, the DQ side where things come out between a producer and consumer. And so what's our dream? Our dream is going to be we want a queue, does the queuing properties. We want to parameterize both the depth of the queue and the data type. Both of those seem like pretty necessary things to parameterize. So those don't seem like things we kind of can hide from the user. And we may have certain, power performance area goals. In other words, efficiency. So how can we take this, ambitious goal, and make it something we can go start writing code for right away? Well, let's think simple. How can we somehow defer some of the features to later and do simple stuff now, right? So maybe instead of having a parameterized QDEF, we can have a fixed QDEF, right? Same thing for data type. Rather than having arbitrary data types, what if we fix the data type? Okay. And how about performance? Well, what if we make it slow, but hopefully correct, or at least close to correct, and we'll kind of go from there. Okay, so how do we do that? Well, let's make a really, really simple queue. It's going to be a single entry queue. It only has one entry. No parameters for that. But what is it going to do? It's going to implement the interfaces, right? It's going to implement this NQ and DQ, which are both these decoupled interfaces, which have, both bits and the ready valid stuff. And so you can imagine if we're able to get this thing working, we can build all the stuff around it, right? We can build, test benches to expect all the stuff. And as we improve this queue, hopefully this interface is going to stay the same, right? And so that's we can kind of reuse all that stuff we're building. In terms of the exact details, to make this as simple as possible, we're saying, yeah, single entry. We're not going to do that flow optimization, so we can bypass the queue if it's empty. Not going to do that. Try to make it as simple as possible. We are going to have one tiny thing for the pipe feature. Okay, if it's uh, if it is full and we're both NQ and DQ at the same time, sure, we'll allow that. So it is technical optimization we could, defer, but you'll see in a second it's not so bad. So here we are trying to draw what design would look like, and we can imagine, okay, well, we'll need, you know, some register to hold the actual data, and some register to kind of hold the notion that there, some metadata about how much data we have, right? And then really kind of the unknown at the beginning is, of course, what logic goes in here. Some combination of logic to figure out how to do the ready valid signaling in both directions. That's kind of what we got to figure out. Okay, well, let's go ahead and code this up. For today, to get that reuse we're talking about in terms of writing this once and continually reusing all the interfacing, I'm actually doing that with inheritance. So we'll come to inheritance in the next lecture. But for now, you can just kind of suffice to say everything's going to have the same I/O pattern, right? It's going to have the same number of NQ decoupled, DQ decoupled. So even though it's written like up here and then down here, it's the same thing. We can see, for example, we have a Q depth of 1. Okay. We parameterize a bit with because it's really easy, but that's not essential. But here's the key thing. Okay, the data path, right? We have our entry for the single register and this full bit. So we go back a slide. We can see, yeah, there's our register. There's our full bit. Cool. All right. Then we got a lot of things to connect up, right? Why don't we trace the data path first, right? So the DQ comes out of the register, right? Entry, sure. The NQ bits come into the entry, but only when it fires on the NQ, which kind of makes sense. Remember, firing on the NQ means both ready and valid are true. In other words, we have space tick something here and something legitimate is coming in. Okay, that makes sense. But then we got to, handle all the arrows coming out, right? How do we do NQ.ready or DQ.valid? Well, NQ.ready is either if we're not full, that makes sense. Okay, if we're not full, we have space, sure. Or if we're DQing. If we know we're DQing, there's going to be space next cycle. That's that pipe optimization we were talking about. Okay. How about if the DQ is valid? Well, the DQ is valid if there's something in there, right? If it's full. Okay, cool. And then what's the remainder of the stuff here? The remainder of the stuff here is actually control that full bit, right? So you can see, for example, when we're DQing, and remember, in order to DQ for that fire to actually happen, that means ready and valid for DQ are true. So for ready to be true, that's something from external to this module. But for valid to be true, that means full itself is true, right? So, remember this is, the same as ready, uh, ready.dq.ready and io.dq.valid, right? It's the same thing, right? Um, So I said the uh, valid is already means it's full. So we need to unset this thing, make it false because yeah, we're emitting it. Now notice if something comes in at the same time, we're then going to set full to true. So that pipe behavior we're talking about is implemented by this. And because, of the last right winning, last right semantics, the second modification to full is going to win. But for both this example and for today, like I said, the emphasis is not just on the chisel code itself, but also on the process, right? The process is we made a really simple queue. It's not technically the simplest. We could have made it a touch simpler, but it's pretty simple, right? Single entry, not very spiffy, not very parameterized, but it implements the interface, right? There's ready val signaling on both sides. Okay, cool. We got that. And off screen, we got this correctly implemented syntax wise. Here is that queue model from before, which I'm not going to go into tons of detail. But yes, we had all these various scenarios about how to work for a model. We've covered this in a prior lecture. And then we also have the ability to take our model and plug it directly into a design. Sure. And yeah, um, cool. So then remember I was talking about testing, right? I talked about testing. We had to have both inputs, a notion of what's correct, and a way to kind of plug it all together. And this is the co-simulation methodology we have in this course, right? We build a model, prior slide. We have the model integrate with design in this sim cycle function. And then we actually have a test, which in this case, there's a few cycles, and you know, it tries in queue one, two, and three. While it's in queuing the two, it's not dequeuing, so there's no room, and thus that two is lost because it doesn't try again. But this kind of shows it's working, right? Okay. So questions so far. So yeah. So I mean, see how even though we've been building a really simple module, it wasn't trivial, right? We still had to write up some test-based harnesses. We had to kind of think about this, right? To kind of think about from the beginning, okay, well, what am I going to want to test this? Okay, I want some sort of test bench where I can kind of NQ and DQ and maybe get this interface right now, even though it's hard to get right, but try our best to get it close to right at least. And then make the internals simple, but there's still a lot of other collateral we get to worry about. Okay, so how did this do? Well, implements the queuing behavior, implements decoupled, that's great. We had a parameterized data width, that was easy. So it's, a gimme, right? Wasn't lack? Well, only one entry. So we want to have this actually be parameterized queue, parameterize the depth. So architecturally, how can we do that? Well, we could build one of those shift registers, right? Remember the delay pipe we had earlier in this quarter? Sure, we could have a shift register where, we parameterize the number of entries and we have these shift registers here for the data. Perhaps we have a corresponding set of, full empty bits to track if those entries are valid. Sure. And so yeah, so you can kind of see this comes together, right? Just, data path of these full bits going down, the entries going down, and then some combination logic we need to implement to actually do the ready valid signaling based on all this. But we'll have parameters, in green for, number of entries. You can see, oh yeah, things come in at one end and come out the other end. So this seems to be a step in the right direction. Let's see if we can code it up. Um, so remember I was talking earlier about how we're using this inheritance to kind of hide repeated code. So you don't see the IO here because it comes from the inheritance, which I'm going to cover in the next lecture. But for now, you can just see, sure, here's the body of our queue. The IO is unchanged. We have those entries, which is going to be a sequence, of num entries of the registers to hold those bits in data path. We also have the full bits. Okay, that's implementing those registers. Our chisel at the end of the day is just implementing things, connecting things, right? So here, implementing a bunch of registers. Okay, and then what's the middle pieces here? Well, there's this notion of when we want to shift down. We'll worry about the logic in a second, but for now, let's say we are shifting down. What does that mean? Well, for the entries, we kind of want to connect to the prior entry to kind of move things down. Cool. So if you go back to the prior slide, you may have noticed I had this like gray text for head and tail. So in Scala, when you have collections, things like seek or even more general collections, there's a notion of head and tail, right? So head is the very first element, tail is the very last element. Just make it clear how I'm choosing to map this to this design to put the head on the DQ side. So that means This is, index zero, this is index, n minus one. Um, cool. Okay. So you kind of see those pieces fit together. And then in terms of like the actual endpoints of this, shift register, well, if we're shifting down, we're kind of in a way putting a bubble in the back of the pipeline. So it makes sense that the last full bit should be set to false. In other words, there's not a legitimate data there. Meanwhile, on the NQ side, okay, yeah, for NQing, of course, we should be putting data in the last entry and marking the last entry as true. So what are the remaining parts here? Okay, well, we're ready to NQ if either the last entry is not full, i.e., it's empty, or we're shifting down, in other words, making room, right? Okay. Um, so uh, when will we shift down? Well, if we're dequeuing, sure, something's coming off the end of it. Or if somehow we encounter an empty entry, meaning, we have somehow, this is being marked as empty, we might as well ship this thing off so you kind of can move on to something behind it, which hopefully is useful, right? So, okay, that's the conditions for shifting down. Um, you can see, of course, we're ready when last entry is free and we're shifting down. The output is valid when simply just the last entry has something. The bits, of course, is the last entry. You kind of see how this fits together, right? So this is like I said, you couldn't write this in 2 minutes, but maybe in half an hour and a little bit of trial and error to come together. Um, Interestingly, you can implement all of this effectively, not exactly the same, in 2 lines of functional programming. Now, once again, we can always have this debate if we think this is an improvement or a step backwards. Um, in this case, you remember in the original code, we kind of had these for loops where we're kind of going through the entries. We're doing that here with a fold right pattern where, you know, what we're doing is using the indexing here to kind of be able to reach between, I and I plus one. With the fold pattern here, we're, recording the last entry. So that way, when we get called the next time, we have both the current entry and the last entry. So how do we get the last entry? A little bit sneaky here. We are connecting the two of them together, and then we're passing on this entry with the fold as the result to be, becomes the last entry next time it gets called. And so you haven't seen this all quarter. This is a semicolon, right? Crazy world. But yeah, so the semicolon makes it clear that these are two separate statements. So this is statement one, which is, due to connection. Statement two is simply just saying this entry, and the last thing there is going to be the things returned. So that's how we kind of get that pattern of the last entry. You may notice how we have this notion of fold right, and that's because the DQ side is from zero, so we kind of want to connect up this way. Question? Yeah, that's a great question. So if we flip the order of these statements, would this break? I think so. No time like the present to find out. So, of course, it runs now. I can show you in a test case it's going to run. And now let's see if we break it. Um, what this boils down to is by changing the order of these statements, this, of course, doesn't really do anything. This statement does the side effect, and the question is, what is the return value of that line? If the return value is this entry, then perhaps that'll work just fine. So let's see what happens. I think it's going to be maybe void or unit, I guess, in which case it's going to break. Yeah, so it's unit. So the connect statement has no return type, right? A connect statement is just a side effect intended statement. It's kind of, chisel imbibing the Scala philosophy of, making it really clear what's what. And so by having that connect operation not return anything, and it's, breaking my notebooks, we can do that. So yeah, I'm gonna have to, undo that change. But yeah, good question to kind of get across that key issue of um, what's going on here. So we want this side effect, and we want this thing to be returned. And because we're using, fold right rather than for each, yeah, we are trying to return something, right? We are returning this reference to kind of passing around. Yeah, so not so much after a semicolon, but in any code block, whether it be a function, a class body, a if statement, the last line is the return for that thing, right? And so, yeah, in this case, we want to return this entry. And so we do that. The return keyword actually does exist in Scala. It's rarely used. You haven't seen me use it. uh, the advantage to the return keyword, rather than making the last line of the function return something, is that way you can return in the middle of a function, which, you know, sometimes that makes sense. Sometimes you can structure your control logic such that it's always the last line. Yes. Oh, good question. So it's not so much a chisel doesn't declare the return. This is me using functional programming, right? So me using functional programming, trying to be slick. Here I have an anonymous function, right? And my anonymous function is trying to be concise, right? I'm trying to do this. I could do a full-on, proper function, right? Hey, def, uh, calls me to connect and pass, right? I don't know. Um, and what will this take? This will take this entry and last entry, right? It's going to return uh, a uint, right? And then uh, internally, we are going to do this, right? And then I can, in theory, replace this, fingers crossed. You know what? I'm going to leave off return type because I might have gotten the syntax wrong. Oh, these don't have types. That's on me. Uh, didn't break. So yeah, you can kind of see, right? If the anonymous functions ever look too gnarly, stop, right? You can just write a regular function. Um, or maybe the for loop's more clear, right? Like the goal is to have code that someone can kind of read through and directly understand what's going on. If someone's kind of spend 2 minutes kind of scratching their head and staring at it, scrolling up, scrolling back, getting help from their IDE, copying and pasting in another window, ChatGPT, what does this code do? That's not a good sign, right? Go ahead. Yes, exactly. Yeah. So semicolon, when I use it down here, is basically just putting this on 2 lines. Correct. That's why I was there. Great questions. Yeah. It's kind of fun, of course, to play around with code and see what happens. Cool. So yeah, so we built another version of our queue, right? It works to some extent of working. Um, so we're able to kind of go too deep, sure. Um, let's take score. So still plus queuing behavior. And now we parameterize number of entries, right? So that sounds pretty good. Perhaps even done, right? Not quite. So if we go ahead and analyze our queue, what do we see? Well, performance is not good, right? In particular, with our architecture, every entry that goes through the queue has to go through all of those registers. In other words, I could have an empty queue. The queue could be empty, but has capacity for n registers. Guess what? Everything that comes through there has to have at least an n cycle latency to get through, right? And that's kind of silly. So even if it's empty, the latency is high. And as I said before, right, you can imagine, maybe it gets filled up, maybe there's some bubbles, and you put some more stuff in there. I try to drain the bubbles with things like, shift down when, the last thing's empty. I can't promise that's perfect, right? This is maybe a little buggy. So we have some concerns about how this thing handles bubbles, and latency is not good even in the best case, right? Because imagine the latency, the queue should be proportional to how full the queue is, right? Not how big the queue is, period. Yes. So remember, good question. The question is, why do we get bubbles in the middle? So if I go back, imagine I enqueue something, and right now it's all empty. I enqueue something. So it's going to want to move that to the other end of the queue, and so it's going to keep putting in bubbles behind me as it goes down. Yeah. It's not so much because it's asynchronous or synchronous. It's more just because even perfectly synchronous, the issue is, yeah, data has to come in and go through all of the registers before it come out, right? And so it comes in, and there's no data coming behind me. There's going to be a bubble behind me immediately, right? And so the bubble behind me, does this logic do the right thing, kind of squeezing those bubbles out, right? Um, so yeah, that's the concern. So we have, these full and empty bits tell us what's full or what's empty. Um, but yeah, it's going to be, hopefully that's correct. So yeah, so this queue, like I said, it could have bubbles, could be long latency. Okay, so you can kind of see where we're at though, right? We worked really hard to get a foothold with our V0 queue. Our V1 queue now has some of the parameters we were seeking. It's just not as optimized as we're hoping, right? So we're going to kind of keep incrementally going at this, figuring out what's it going to take to get optimizations we want to get to where we want to be. Okay, so these bubbles. Well, what if instead of putting everything in at the end, we put it into the first free slot? So if the queue is empty, heck, we can put the data right into the last entry so that way it's able to come out right away. But if some of these are full, sure, we'll put it in the first free slot. So that way there'll be no bubbles between that. There'll be continuous, full data and then empty capacity and nothing in between, right? That sounds pretty cool. So how would this look? Well, we would still have a shift register because potentially this queue is full and the data shifts its way towards the end. But the key part is, the data can come in anywhere where there's a free slot. We won't put it in particularly into the first free slot. How do we find the first free slot? Priority encoder. We covered that a week ago, right? We actually put it to work, right? We want to find that first free slot, textbook priority encoder application. Got it. How does the priority encoder know what's available? Well, we have to still have the full bits per entry. So if given it knows which ones are full, which ones are empty, that goes into the priority encoders, can turn on the first one is free, and then the bits are going to get routed to there. And like before, we got to do some logic about how to do ready valid. Cool. Okay. So V2 doing this. Guess what? The data path is still largely the same, right? We still have our, registers. Notice how before we had a seek of registers, now it's a reg. Sorry, it's a vec. It's a reg of vec. The reason why it's a vec is because we actually are going to want to, in hardware, dynamically index which one we're going to, right? That's what priority encoders are before. So we're going to need that vec capability. Okay, so we have the vec capability for both of these. Cool. And then we see some kind of interesting code. So for example, we have these registers indicating if it's one, that means the corresponding entry has legitimate data, i.e. it's full. So for writing someone's logic out, I thought, gee, wouldn't it be nice to be able to say something is empty? So it's just the negation of that, right? Okay, if something is not full, it's empty. So how can I do that? Well, I could take the full bits and just basically map them all to the not symbol. So once again, the functional programming, extremely concise, right? So if you and your readers notice functional programming semantics, this is probably more clear and more concise than doing it the long way with a for loop or something. So this is a case where I think it's a good use. Um, so for example, uh, how do I know if I'm ready to enqueue? Well, the question is, are there any empty slots? And well, I could take the empty bits and simply say, is any of them true? If any of them is true, I can do reduce, right? I can just OR them all together. Okay, cool. How about if I'm ready to DQ? Well, is that last entry full, right? Is it full? Cool. And the bits for the DQ, sure, comes right off there. And then when it comes to, DQing, if the DQ fires, what happens? Well, that last entry is now empty. And then I'm going to go ahead and shift everything down. So what is, I plus one now becomes I, right? And so you can see how, for example, this kind of plays out. Uh, and so I'm shifting in the emptiness at the end, and everything's kind of shifting down. So, using these paths here to shift everything down. My initial notation uses for loop. Like I said, make it simple, get it right the first time. And then I didn't even bother in this case trying to use a fold right pattern to do this again, but you can imagine trying functional program if you really want to. And then for the enqueue on the other end, now I'm going to put a priority encoder to work. So give our priority encoder the empty bits. We want to find the lowest index empty location. This is the current free index. And then that's where we're going to write to. And then the entry at the right index, we're going to go ahead and put the bits in there and mark it true. this mux is actually a fun little detail. So, uh, you think the priority encoder tells you, if you go back a slide, priority encoder says, hey, this one's free, so I should write here, right? Uh, that's close to right. If I'm if this is not shifting, yes, I should write here. If this thing is also simultaneously shifting down while I'm enqueuing, that free slot's moving down one. So I need to subtract one from it. So this is kind of a subtle bug. But it was found actually by one of the guest lecturers you're going to see in a few weeks, Kevin Laffer, who's going to talk about verification. And yeah, he ran some verification on these codes and found, oh wait, there's a subtle bug here, and this is kind of fun that we obviously know we can point to. Um, and so yeah, so this is a subtle issue where if we're dequeuing, if everything's shifting down, we subtract one from the free index. Otherwise, it is the right index. It's not shifting. It's not moving. Cool. Questions? Okay. Go ahead. Oops. Make sure. Yeah, and then we go ahead and test it. Yeah, it works. We're not doing super rigorous in these test benches today, but you can kind of see, yeah, we're enqueuing, dequeuing, things are happening. Um, how do we do? Well, we put community behavior like before, parameterize data with number of entries like before. Cool. Key thing about this whole using the priority encoder, right? The latency to get through the queue depends on the occupancy, right? In other words, if the queue is empty, I can get through this queue really fast. If the queue is full, it takes me time to get through it. But that's fundamental. It's kind of hard to avoid that. It's better than our queue V1, which the latency was always long, even if it was empty. So what do we not like about this queue? Uh, as written right now, we can't use that pipe feature. We can't simultaneously enqueue and dequeue into a full queue. If there's some free space, yes, you saw this code from before. We can enqueue and dequeue simultaneously, but if the queue is completely full, when that pipe equals true feature is normally enabled, right? We can enqueue and dequeue in a full queue. We can't right now. How about power? We haven't talked a lot about that in this course, but if you go back to that design, think about this thing, right? We have all these registers, and if it's close to full, data's being written here and working its way through here. That's a lot of bits toggling. Every cycle, a lot of bits changing. It's going to be a lot of power consumed. The question is, can we figure out a way to have fewer bits and fewer wires toggled? And then what about critical path? You can imagine if this queue is only 2 or 4 deep, this priority encoder is pretty simple. Remember from before, right? We went to priority encoders either with the muxes or with those AND gates. Instead of having a 2 or 4 entry queue with a 512 entry queue, that's a disaster, right? A 511 input AND gate. Obviously, the cat tools will break up into bite-sized pieces that are 2 and 3 input AND gates, but it's going to be a very deep tree for just one of those terms, right? That priority encoder is going to become a real critical path in a hurry for a high number of entries. That's not going to be very scalable. But hey, this is why it's good to do the agile process, right? It turns out maybe if you're a team, you plug this module into your entire design, so some other team working on other parts of your entire design, and to say, you know what? Uh, it's not the critical path, so we don't care. We only need to be 4 entries. It's not the critical path. Great, you can stop here. But maybe you say, you know what? I need 120 entries, and you put it through tools, and tools tell you, yeah, 120 entries, that is definitely the critical path. Or maybe put it through the tools, and it says, you know what? This thing burns up more power than we would like. Can you bring that power down? So now that you know you need to do this, we can go ahead and figure out how can we solve those issues. How can we solve this critical path? How can we solve the power issue? And this other one is a small detail about, how can we simultaneously enqueue and dequeue on a full queue? Okay, so one idea you might have is, what if instead of, having a shift register, rather than moving where I'm moving data, always having a single exit point, what if I can put data into and out of the queue at arbitrary locations, but to keep the data doesn't move, right? In order to save power, we're going to write the data once and leave it there until it leaves. That's the key idea, right? So we're going to change where we insert, where we remove, right? In other words, where we enqueue, where we dequeue, but data's not going to move. Data doesn't come in once, be written. It's going to chill until it's time to leave. And so how does that work? Well, this is a classic thing throughout systems and hardware called a circular buffer. In other words, take a 1D array with 2 pointers, and we keep track of things. So to implement the queuing behavior, it does what we want, right? The whole point of a queue is first in, first out. As long as we have that same order, we can do it in various ways. And so with this way of doing it, so we want to dequeue something. Well, whatever the out pointer points to, we take that element and then we add one to the out pointer. Meanwhile, if we want to enqueue something, we put it where the in pointer points and we add one to the in pointer, right? And so you can see how either way, these pointers in and out keep having one being added onto them whenever these operations happen, whether it be NQ or DQ, and they, grow. At some point, so a circular portion comes in, they need to wrap around, right? So this is, whatever this Q size is, whatever you're always gonna be adding, plus one mod the Q size. If the Q size is a power two, this might work out naturally for you. But if it's not a power two, there's gonna be a mod operation there to kind of make it wrap around, or at least a comparison and an unwrap function, right? So when you get to the end, you wrap around. So okay, that seems like a pretty cool idea. How do I know if it's empty or full, right? Like how would I know, right? How do I know that what out is pointing to is legitimate data? How do I know that what I'm trying to write in is empty as opposed to full of something? Well, for now, let's make it simple. We'll say if both the in and out are equal, the queue is empty, right? If in and out pointers point to the same location, nothing's there. If we get to a situation where in plus one equals out, we're gonna call that full. So you might be saying, wait a second, if in plus one equals out, wouldn't that mean we're losing one entry? Yes. Yes, we're losing one entry. Defer that. We'll come back to that later. But for now, yes, we'd be losing one entry. But hey, we're getting a foothold. This new idea, we're building the circular buffer. It's the kind of thing, like I said, the circular buffer idea pans out. You implement this new approach. Hopefully, you see a reduction in critical path. Hopefully, you see a reduction in power consumption. If that's encouraging, then you have motivation to go forward and figure out this issue about using up that last entry, right? And maybe that last entry doesn't matter. Maybe you have 120 entries. Losing one entry you don't sweat, that's fine. But if you have only a handful of entries, maybe you care. So like I said, to what extent you can defer the heavy lifting until you know you need to do it, right? Um, cool. So how does this come together? Uh, the entries themselves for the circular buffer, it's going to be, a vec of reg, and needs to be a vec because we're indexing into it dynamically. For those indices, those are going to be registers as well. There's going to be no number, right? An index, right? What index into this vec is it going to be there? So we have both an NQ index and a DQ index. And using the logic I just told you about from the prior slide, right? We're going to have it's empty when the two indices are the same. And we're going to say it's full when NQ index plus one equals DQ index. Now you may notice I didn't really do the wrap. The way I'm doing the wrap for now, for simplicity, is I'm just requiring the number of entries to be a power of two. And because it's a power of two, of course, with binary arithmetic, and you add one, it's going to automatically wrap around for us. Um, this is an example of, once again, of a way to make a simplification to get started, right? This wrap logic can obviously be solved in the future, but I'm not going to worry about it for now. Making reconstruction, right? Hey, if, power two still covers a large range, right? So, maybe the final design is going to want to be a 40 entries. Okay, well, if I can push 32 and 64 through the tools, that can still give me a good sense of where I'll be on track for 40, right? And so look for these opportunities to have simplifications to get started, get things working, and then incrementally take these small steps at a time, right? And so you can imagine going from a power tuner of entries to a non-power tuner of entries. That's going to require some changes to the logic, but that's a much smaller challenge than trying to do it all the first go, right? Take these baby steps, go incremental. Um, cool. Okay, so now we have this kind of notion of empty and full. How does this help populate things? Well, we're ready to NQ if we're not full, right? We're ready to DQ if we're not empty. Or valid, DQ is valid if we're not empty. That's pretty simple. How about the bits? So how do we write things? Well, for DQ, we simply just read from the DQ index. Cool. Of course, if we're DQing, we add one to the DQ index. Like I said before, because power tuner of entries, this does the wrap for us automatically. And what about NQing? Well, we NQ at the NQ index. That's pretty simple. And we also do that, right? Technically, I could pull this into this one statement for symmetry, and maybe it makes people happier to symmetry. But really, there's not really a risk in leaving it outside, right? Like reading a register is not damaging it, right? The reason why for NQ we have to do this is we don't want to, change the contents of the entries unless we're for sure doing it, right? But this read, of course, over here is non-destructive, so we can leave it on the outside for simplicity. But yeah, for a person that wants a symmetry, you could probably sink it in there and see the cost for the hardware, and I think it's not much more. Cool. Questions? So yeah, you can imagine where we started from, right? We started with single entry queue, went to a shift register of a priority encoder, and now also a circular buffer. So you can see our microarchitecture keeps changing, right? But the big picture is not changing. The big picture of implementing a queue, what does the interface look like? That's not changing. We're able to reuse those test benches. The rest of our teammates working in other projects, part of a larger design, can still interface with our module, still push us through the tools, and still see things, right? And that's kind of the point, right? Is that we're not just, this gaping hole in the design until this is done, all of a sudden it's supposed to be done and perfect. They have something, right? And we're trying to keep improving this thing that, hopefully can be smaller, more efficient, you name it. That's a kind of agile incremental process at work, right? Cool. So yeah, go ahead and try it out. Sure, it works. It does queuing stuff. Um, so take score again. It's a queue, right? Parameterize data with the number of entries like before. Like the priority encoder based one, latency based on occupancy, that's really good. But unlike the priority queue one or V2, it's more efficient, right? There's less bits toggling, right? We simply just write the data once and it stays put until we pull it back out. And in general, those indices, right? Those are log base two number of entries, right? Those are not very big counters. They're kind of changing around. So it's a lot more efficient for that. Also, the logic's shallower, right? Remember before for the priority encoder, as we add more entries, that priority encoder gets bigger and bigger and bigger, right? In this case, when we get more entries, that vec of registers gets bigger, sure, and the counters get a little bit bigger, but they grow logarithmically, right? So it's not that bad. What are the shortcomings? Well, we have a few of them, right? And these are kind of subtle performance details. You can see that, yeah, we can go ahead and fix these. And perhaps, depending on the needs of the entire project team, either we do or don't need to worry about these, right? So, for example, for detecting if we're full, we kind of have that +1 condition we're talking about. So that kind of causes us to sacrifice one entry. So if we have, n entries, we actually only can use n minus one of them. So we're losing one entry. Maybe that's not a problem. Maybe it is, depending on our usage case. Or we also use constraint I did for simplicity of the number of entries needs to be power of two. I did that and do the wrapping for us automatically. You can imagine I could do that, remove that constraint, and then do the wrapping more gracefully. And then performance wise, uh, like the prior one, right? If the queue is full, I can't simultaneously NQ and DQ. We imagine that's possible when Pipe is true. That's the goal. But like as it is right now, it doesn't quite have that functionality. It's a good thing we can go ahead and address, right? So how do we reclaim that last entry first? We need to differentiate the case of when it's full and empty. Like I said, if you have the indices pointing to the same location, how do you know if it's full or empty? Well, that's a subtle bit of information. Why don't we just add a single bit of state called maybe full to capture this corner case, right? So you can see, okay, if the indices are equal and maybe full is true, we're full. If the indices are equal and then maybe full is false, i.e. not maybe full, we know we're empty. And indices aren't equal, uh, we could be full. We're not full or not empty. So we're somewhere in the middle, right? And at that point, we don't even need to look at the maybe full bit. So I didn't even bother writing in that line because we don't need to actually look at it. So really what matters is only when indices are equal, we're using maybe full to differentiate between full and empty. Okay, so given that goal, take the code from before, and now we just maybe full, so it's another register, and you can see that logic I told you about a second ago, right? We're empty when indices are equal and maybe full is false. We are full when the indices are equal and maybe full is true. And this other stuff's kind of unchanged. However, we have to add some logic to control this maybe full bit. Okay, so what is this logic? Well, when we're dequeuing and the indices aren't equal, we're just going to say uh, make maybe full false. Meanwhile, if we're enqueuing, indices will become equal. So you can see, for example, right here, enqueue index is going to be enqueue index +1, but of course it's a register, so that value is available to the next cycle. So the new value of enqueue index, if that's going to equal dequeue index, that tells us we're going to have these two things be equal. And because we're going from not full to now adding one and becoming full, we're going to remember that maybe full. Like I said, this logic may not be trivial to get right the first time. This is part of why we want to do a baby step at a time. Yes. Yeah, I mean, so yeah, from recording put this down, there's a description of an alternative way of how to resolve this full empty issue for queues in another digital design course in 125. I don't know the particular slide by heart. There's all sorts of ways to design these queues. Um, when it comes down to it, right, uh, there's the high level performance metrics, which is are able to use up all of our entries and that kind of stuff. Whether we have 1 bit extra or 2 bits extra, that's immaterial, right? What matters more is uh, can I get this logic correct? Is it correct in all the corner cases I care about? Um, I think the solution you're describing, I can't imagine that having a worse critical path than what I'm describing here. So I think it's the least comparable. Um, I don't know if this one is faster or slower critical path wise, but these auxiliary bits, these are kind of, probably not critical paths. Critical path probably is the wide bus coming in going to the registers anyways. But it's a good question. I'd love to see that lecture. I can track down Professor Richmond and ask him how he does it. Um, cool. So yeah, we can go ahead and like before run it. So now we're able to reclaim that last entry. We had 4 entries and we can use all 4. So yeah, less bit shifting and we can now use all of them. Cool. What are we missing? Capacity still needs to be powered to can't simultaneously NQ and DQ to a full queue. Okay, let's keep going after it. So let's do the simultaneous NQ DQ when full. Um, so what does that require? Well, it requires us making this change right here. So if you remember before, it was simply we were ready to NQ if we were not full, and if we were full, it would not let us NQ. Now we're saying, you know what? We are totally ready to NQ if we're not full, sure. Or, if we are full, i.e., not full, then this or comes into play, right? If the DQ is ready. So it's actually not too crazy, right? Okay, so why did we not do this in the beginning? Well, as you see in this note where I'm warning you, then now there's a path from DQ.ready all the way back to NQ.ready. So our DQ.ready comes into our module. NQ.ready is an output from our module. So now we have a path going through like that. And depending on how the rest of your topology of your design is, this could also make a combinational loop, which is why pipe is not, always on for the queue and as a feature turn it on or off. We can imagine we do something similar. We could have a pipe parameter and we could decide, you know, actually I'll do this right now. Oops, ooh, pipe is going to be, you know, Boolean, right? And like we saw in the homework, right? You can imagine, if pipe, we're going to do this, right? Uh, otherwise, you're going to do just that, right? So you see how this is the kind of power of a hardware generator, right? Where we can, with a little bit of Scala mixed into our chisel, we can have this pretty cool parameterization, right? Where it's kind of fundamentally changes this queue, right? Where it does have this extra path, but it comes with the efficiency benefit, or does it not have it, right? And we can kind of easily do that. Um, but yeah, so in general, this wasn't the most invasive of changes to do what we described to have the ability to NQ into a full queue if we're DQing at the same time. So yeah, here we have it only a 2 entry queue, and you can see us kind of putting things in and putting things out at the same time, and it's totally happy. Cool. So you can see piece by piece, making this queue better and better. And you see how, at V3, we already had something pretty close to the final product. Arguably, V2 may have been sufficient depending on our use case, right? Um, and so, you know, keep evaluating, keep assessing, and deciding what is needed, right? If you look at your entire design holistically, so you know what? Right now, this queue is not consuming too much area. It's not consuming too much timing. We have bigger fish to fry. As a design team, we should work on other project instead. Do that, right? It's like don't go 100% of something until you know you need to, right? Um, so how do we do? Well, we can now NQ and DQ in the same cycle. All those other things are good. We've been doing great. What are the downsides? Well, our fix on the last slide added this combination loop potentially in there. That's not great. Also, the capacity needs to be powered too. So let's see if we can go ahead and fix some of these. Let's fix the capacity, or we're going to do both at the same time. So how are we going to tidy this up? Well, like I just showed you, right? We could write this behavior, right, of pipe like that. So that way the combinational path is there or not there, depending on what we need. Okay, what else happened here? I changed these indices to be counters. So here they were acting like counters, right? We basically were adding one to them, not adding one to them all the time, only adding one to them in certain cases, and we wanted them to wrap around. So guess what? If we just use the counter concept, we get all that, right? The counter can take a number of entries, and we can tell a counter, hey, I want that counter to increase by one, dot inc for increment. Um, Notice how I don't have to have any logic in here about doing wraparound because the counter does it on its own, right? If it gets to the maximum value and you tell it to increment, that counter module which already exists is going to do that for us, right? And so, yeah, this is a better design, right? We are putting less complexity into our design by leveraging existing tested abstractions, right? And this counter abstraction makes sense. So I'm reading this rather than having to kind of figure out what's going on, like, oh wait, so and so declared a register, this value is zero, and has certain math about how big it is, and then I see them adding one to it, and oh wait, there's this details of power too. That's how does the wraparound. That's a lot of concepts to figure out when you're reading it, right? Versus using a counter. Hey, number of entries. Someone knows a counter is going to be increasing and then wrapping around. That kind of all comes together, right? And you see a lot of this code gets simpler down here. Another thing that kind of comes up, which is maybe not immediately obvious, is that uh, this simplification for maybe full, which I would say is not obvious when you first look at it, but what are we saying? Okay, if I have a situation where the fact I'm firing on both sides is different, in other words, I'm enqueuing but not dequeuing, or I'm dequeuing but not enqueuing, what does that mean? Uh, that means the number of elements that are active in my queue is changing, right? If I'm firing at the same time on both sides, or I'm not firing on both sides, the number of active elements is unchanged. However, if I'm firing in queue but not dequeuing, that means the occupancy is going up by one. If I'm dequeuing but not enqueuing, it means occupancy is going down by one. So this cleverness is to recognize, wait a second, I can just compare these situations and I can mark maybe full to be the case when I'm enqueuing. So in other words, if I'm enqueuing but not dequeuing, that means we're increasing the capacity utilized, right? I can mark maybe full to be true. Doesn't mean we actually are full. We're saying maybe full is marked as true, and if eventually the NQ index equals DQ index, it's gonna be marked as full. I chose to break this up more at the code and make indices equal to kind of show the logic reasoning here. Um, this replacement of having instead of having two equals tests here versus having this individual signal there, that's not going to have any noticeable change in the hardware. Not because it's small, but because it's called some common self-expression elimination. Tools do it just fine. They will figure it out on their own. They will figure it out. But I did as a human, I did a common self-expression elimination manually because maybe it makes it more clear the intent, right? We're saying, hey, the key thing is these indices are equal. By labeling this comparison and using that label, someone reading this can perhaps better understand what's going on here. Cool. Questions? We can go ahead and run it. So yeah, notice how because we're using the counter, for example, like does the wrapping for us, we no longer need to worry about power two. I also slipped under the rug, used a mem rather than a vec of reg, right? Which reg of vec of say, which mem can handle a lot of these cases pretty well. Pretty much the time, if you need multi-registers, mem is great. Remember, mem is not the same as a SRAM. Synchronous read would be a sync read mem, right? So mem just by itself is collection registers and mux attached to them. Mem works great for a lot of things. The time when you need to use a vec of reg rather, or I should say reg of vec rather than a mem, is when you want to do like global instantiations all at once. If you want to do like a reg in it, then you use the reg. But if you're not, just use the mem. So the mem is tidier, where I can just say, hey, number of entries, bit width, does all that for us. Cool. So yeah, it works. How are we doing? So queuing behavior, parameterized, latency based on occupancy. It's efficient, not very bit shuffling. Can now enqueue and dequeue in the same cycle, optionally, depending on what we want to do, and support non-power two member capacities. That's pretty spiffy. So what are we missing? Oh, how do we add flow? No, I'm not. So that's a good question. So the question is, if we want to add that flow parameter, ability to bypass the empty queue, what would that look like? Good question. Let's take a look at the code. Um, so it would be some sort of logic based on recognizing we're empty, right? We're not going to be modifying the counters, right? Because we're not writing to the actual queue. We're bypassing the queue. So you can imagine it'd be some sort of, mux here, perhaps, on the DQ bits, right? It's either the DQ index uh, or, not or, but mux. In the case we're doing the flow where the queue is empty and someone's enqueuing and dequeuing at the same time. So in other words, if both sides are firing, so not I did DQ fire. Let's try and write it out. So if we have a situation where it's both sides are firing, right, and we're empty, right. Um, so that's kind of the key condition. So if both sides are firing and we're empty, then I'm going to want to have the io.dq bits equal io.nq dot bits, right? And then you can imagine some ready valid stuff as well. Yeah, you're right. So I would probably, oops. So great question. I think I would cheat and do this, right? And not shown is the ability to turn flow on and off, right? So if flow is true versus if flow is false, you would have some other structures to this code. Um, so you can see how, as I said, this queue abstraction, right? Pretty simple, but there's these different combinations. You got to be code to support all this. There is some complexity to these generators, but the goal is to do it incrementally, right? Rather than doing it all at once, it's hard to figure it out from the beginning. Add these features on piece by piece, step by step. So yeah, basically, what's the only thing we're missing so far based on the criteria put out? Data type. It's a uint, arbitrary width, but it needs to be uint. What if I want sint? What if I want something else? We'll cover that in the next lecture. So that one's not going to be solved. But boom, we did it. We built a pretty spiffy queue. We got there, on a long road, but it was an efficient road to get there that way, right? Where single entry queue, really simple, right? Then we did ship register, but it had a lot of issues. Priority encoder, fixed some of those issues, and then went to circuit buffer, and even we had a circuit buffer, which was a lot better. Kind of getting all those corner cases worked out and those other details took some time, and that incremental improvement is kind of the key point. We had a roadmap where we wanted to get there, and with incremental improvement, you also, of course, can stop at any point if the results are satisfactory, right? You don't need to keep optimizing if you don't need to. Cool. Any other questions? Great.